Welcome back to all our attendees. For those who just joined in, I would like to inform you the contest is still on. Please do go participate in the contest and win some lovely gifts. I now present to you our next speaker, Mr. Issam Said, Manager Solution Architecture and Engineering at NVIDIA Corporation. And speaking on today's topic, the power of HPC computing. Over to you, Issam.
Thank you and welcome to the audience. Today I'm going to share with you our advance that we did within NVIDIA towards enhancing the high-performance computing capabilities from both hardware and software perspectives. You still see my screen? Sorry, just checking.
Yes, we can. Yes, we can.
All right. NVIDIA is becoming more and more as a platform company. Maybe those of you in the audience that know one thing about NVIDIA, they probably know, but heard about NVIDIA in gaming and the capability of actually transforming all the game engine into very optimized tools for accelerating games in general. Most recently, probably 10 to 15 years now, we just discovered that those capabilities can be transformed and used differently. And in particular, how to use those shaders that have been used to accelerate GPU rendering can be used for compute. And this is how we transformed the company from a, let's say, gaming-oriented company into a, let's say, data center company, or I would say compute company. GPUs have been adopted more and more in scientific computing and high-performance computing in particular. Furthermore, with the development of the research in deep learning and machine learning, and also the increase of size of data and problems to solve, we shifted from I would say, a GPU constructor into a system provider. And this is where we actually started to inject more and more GPUs in one server and enhance our capabilities. And very recently, especially when we announced the merger of a company called Mellanox, which is developing interconnect, we became a platform or a system company whereby we're not only addressing the accelerating computing from a single chip perspective or a single node perspective, but from a platform perspective. And we manage all the system from top to bottom, from hardware side, but also from a software stack perspective. Today, I'm going to talk more specifically what we are actually providing in terms of software stack that can be used in all levels. If you look today in NVIDIA offering for high-performance computing, I can summarize it in this slide. From right to left, we go from specific, let's say, very low-level approaches to high-level approach. On the right-hand side, you see the CUDA approach. So CUDA is our API that is used to program GPUs. These are offered to low-level engineers that they are interested into interacting with the hardware and build their software stack themselves. CUDA have been now adopted pretty much by millions of developers across the world, and it's more and more becoming mainstream in code development in general. But we realize that this is not the only audience that are using our GPUs, and this is not the only way of using it. And therefore, we provided different approaches. Basically, what you see in the middle, these are approaches that are different programming models like annotation, or programming languages like OpenACC, for example, where you do a very little changes and your code become accelerated and running on GPUs. And more recently, on the left-hand side, we were working with the programming languages standards so that we can integrate the GPU programming paradigm inside the compilation and runtime process of those high-level programming languages, mainly C++ and Fortran, which means that users do not even have to change their code. And with the changes in the link in libraries, they can actually just benefit from the performance optimization. All these three approaches, they actually rely on very low level APIs and libraries that we put also we provide also to the developers, which are basically our accelerated math libraries. Now, all this is actually gets summarized. It used to be a little bit confusing for a lot of developers. So we just announced very recently that we're gathering all these information in one software stack called HPC SDK. So if you look at this slide here, you would see from development to debugging, we have all the tools needed. We have the low-level APIs, we have the math libraries, we have some core libraries, we have the communication libraries so that you can build efficient and scaling HPC applications, but also you can profile and debug using our own tools. So you do not have to add any other thing needed for code development once you have all these APIs. So let's dig deep into these APIs. So this is just an example of a collection of APIs that we have on math libraries that we have. Maybe the most famous one is cuBLAS, but many others like cuFFT using for signal processing. A lot of developers will just recognize a lot of names in here. So how do we accelerate these math libraries? Each time we come up with a new generation actually of GPU, we just upgrade all the performance of all the libraries to that recent libraries. Not only that, we work on the scaling by providing the multi-GPU support, but also on performance tuning tricks, and then we provide all these information to the developers. Based on that, developers can use this the capabilities of the GPUs, like for example, mixed precision or tensor cores, which is now very famous for deep learning. And here's an example, for example, for math libraries, how to leverage tensor cores to just accelerate performance. This is just an example of DGEM, which is matrix multiplication on the latest GPU generation. And you can see how we shift performance just by just optimizing the software stack. Furthermore, if we add the mixed precision, which is something that very famous in deep learning, we can even increase even further. So all these are actually done by default once you use all these libraries. This is yet another example, and here we can see the impact of such optimization on the library level to the application speed up. I'm showing you here another example for cuSolver, which is a higher level than cuBLAS, and which is actually very famous for linear algebra. And as you can see, with using just the low-level libraries, you can just get the performance out of the book. Another example on cuFFT, which is used for signal processing. And in parallel to that, we just accelerate the communication layer, which is basically how to make sure that we move from one GPU to multiple GPUs. And therefore, we make sure that we provide libraries that can be used to share data between GPUs within one node, or even between GPUs within different nodes. With that in mind, we can participate with a lot of major initiatives and APIs, like for example, OpenSHMEM, which is a low level of MPI, and we apply it to the standards. We just make sure that they are running and scaled perfectly on GPUs without any code changing. You can see here now the impact on application just by optimizing the communication layer. If you add if you add this to the optimization of the core algorithms themselves, you can understand that not only you're accelerating the core algorithms, but also the scalability across the nodes and across GPUs inside the node. And to finish, we also work on the compiler side of things. So basically, you cannot leverage HPC only by using specialized libraries, but also by just simply using the compilers and the programming languages that you're familiar with, mainly C++ and Fortran. And we're integrating the GPU accelerating going forward. We started this effort in 2020 with all these standards, and in particular, the C++ standard. So without going into details, that means if you use your code, your simple C++ code, you can just get the GPU acceleration for free on your system. These are just the scope of work to comply on the C++ standard. And here's are just simple code samples. I will just go very quickly on this, and I'll just share with you this slide to show how you can go from a specialized approach to a very normal approach where you have the same code that you used to use for CPU, and by compiling it differently, you have a GPU acceleration. Not only C++ is our focus, but also Fortran, because we know the HPC community is split between C++ and Fortran. So we're doing the same effort, exactly the same, by just providing GPU acceleration on the compiler level. And we have our own compiler called NV Fortran that you can use to leverage the acceleration without changing any chunk of your code. This is the exact same example on C++. You can see here the ease of programmability just by using the new compilers. Okay, so if you just have to walk away from this talk and remember one slide, that would be the slide. NVIDIA is gathering all the efforts that we're doing in accelerated computing and high-performance computing in one stack. This stack is called HPC SDK. It gathers, of course, the heart of what we do in this field, which is CUDA, the CUDA capability, and the low-level APIs, the math libraries, but also the core libraries that you can use in your different code development, but also all the tools that you need to profile and debug. Not only that, very recently, we just included the GPU acceleration on the compiler level by providing a NVIDIA implementation of the C++ and Fortran compilers. And with that, if you have any question, happy to answer.
Thank you, Issam, for your presentation. Dear attendees, if you all have any questions, please pass it on to us and we'll give it on to Issam. And Issam, please do reply to them, yeah?
Thank you.
And attendees, again, just a reminder, the contest is still on. Please do go to the left side of your menu and click on the contest and participate and win some great gifts. Thank you. Take care.